Thank you very much for inviting me, and this is going to be the first of three lectures. Most of the material will speak to the free energy principle, which tries to address and understand from first principles sentient behavior. So the agenda here is to try and unpack the nature of our perception and action and self-organization from the perspective of physics. However, I'm going to try and tell the story from the point of view of a physicist and then repeat that story from the point of view of a neuroscientist. This perspective, I hope, will be interesting from the point of view of artificial intelligence, certain aspects of machine learning, particularly those aspects that focus on the way that we gather data, that we do data mining, namely the sort of epistemic part of artificial intelligence and machine learning. So this is the first of three presentations. This one is going to deal with continuous systems, continuous in state, space, and in time, to set the scene for more pragmatic applications of the basic principles using discrete state space models in the subsequent lectures, trying to understand a little bit more the mechanics, specifically Bayesian mechanics, belief updating as a way of understanding self-organization. So this talk is going to be divided into three parts. The first part will consider some of the fundaments of the statistics of biotic or life and biotic self-organization, with a special focus on Markov blankets and Bayesian mechanics. And I will try to illustrate the ideas using simulations of a primordial soup and see if we can identify the emergence of self-organization that looks a little bit like life-like organization. I'm then going to tell exactly the same story, but from the point of view of a neuroscientist or a neurobiologist. I'm going to tell that story using the notion of predictive coding and how that might unfold on neural networks in the brain, and then move to conclude with a treatment of action and perception in creatures like us, with a special focus on this notion of epistemic affordance, the things that we find attractive in terms of securing or soliciting the data that resolves our uncertainty about states of the world. But that's going to be the final part of the story. So let's start with a question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? I'm not going to answer that question, but what I want to do is to highlight this notion of a spatial boundary and simply observe that if you want to talk about self-organization, you have to define what the self is, or more generally, what is the thing that is organizing. And if you need to define the thing, then you have to demarcate or separate the states of the thing, say a particle in question, and all the other states of the universe. And Schrödinger probably would be the first person to acknowledge that this boundary is itself a statistical construct. And I'm going to take that construct, that boundary, as a Markov blanket. So for those of you who don't know what a Markov blanket is, I would normally ask the audience to, if anybody knew what it was, and then ask them to explain to their friends what it was. But given I'm sitting over here in the United Kingdom, I'll just tell you what I think a Markov blanket is. So this is a simple heuristic diagram. It's a graph where we can imagine the states of a little universe being denoted by these circles, and the causal influence, the dynamical coupling between one state and another state, is denoted by these arrows or these edges. So these are influences. So this is an influence diagram. And if I were to identify a particular state or set of states and call them internal states, then the Markov blanket is a statistical boundary that comprises the parents, the children, and the parents of the children. And this set of states is a boundary in the sense that if I wanted to predict statistically the dynamics or the evolution of states on the inside, the internal states, given the rest of the universe, I would only need to know the blanket states. So technically that means that the internal states are conditionally independent of the external states when conditioned on or given the blanket states. So everything I need to know about the entire universe is encoded in the blanket states from the perspective of the internal states. And I'm going to make a further move here. I'm going to introduce a bipartition of the blanket states into sensory states and active states in red, simply on the basis that the sensory states influence the internal states but are not influenced by the internal states. Similarly, the active states influence but are not influenced by the external states. So together, we now have a partition that separates internal from external, where the separation is mediated by the boundary or the blanket states. And then if I combine the internal states and their blanket states, I can associate the combined states with the states of a particle. And this particle could be very complicated. It could be a virus or a person, or it could be a very small particle like say an electron. If I can label something, then it must be separable from the rest of the universe, and therefore at some level it must possess this partition, and in particular a set of blanket states that enshroud the internal states. So this diagram just illustrates two of our favorite, or my favorite, systems where that partition can be seen very clearly, where the partition is exactly the same in terms of the conditional independencies that I just described in the previous slide. So for example, in a brain, we would have internal states, the neuronal activity of nerve cells or the connectivity, everything that I would need to know to list or write down the state of the brain at any point in time. These brain states then cause changes or influence active states. They could be my actuators, they could be my muscles, they could be my autonomic reflexes, secreting things into the outside world, the external states, my body or my extrapersonal space, changing the external space states so that they supply sensory states that impress themselves upon my sensory epithelia, my sense organs, that change the internal brain states, and so the cycle continues. So what we have here is a picture where the inside and the outside are coupled in both directions, but through the blanket state. So the outside influences the inside through the sensory states, and the inside influences the outside through the active states. And exactly the same conditional independencies and influence diagram is in play for, say, single cell organisms. So the internal states could be the intracellular states, the active states could be the actin filaments that support and provide motility to the sensory states or the surface states that are pushed into the external milieu, the external environment, that then reciprocate with changes on, say, cell surface receptors to change the intracellular states. And exactly the same exchange between the inside and the outside is seen that we saw in relation to the exchange of, say, a brain with its sensorium and the outside. So What I would like you to do now is to forget about the Markov blanket. What we're going to do next is just rehearse some basic physics of random dynamical systems, and then ask, well, what would happen if we put the Markov blanket back into the equations? So what I've done here is just sketch out a system, a particular kind of system that has a non-equilibrium steady state density, by which I mean there are an attracting set of states to which this system will always ultimately return to. So imagine that there are two states and that the position in state space as time evolves traces out a trajectory on this attracting set and moves around. The key aspect of this is that the trajectory always revisits a certain set of limited states, this attracting set. So you could interpret this at many, many different levels. It could be the very fast oscillations of electrochemical states in a single cell of my brain or body. It could be the evolution of myocardial or heart states during a single heartbeat. It could be me getting up in the morning, having a cup of coffee, doing my emails, having lunch, and going through my daily cycle. It could be an annual cycle with Christmas holidays and summer holidays. It could be a life cycle. The key thing, all these levels of either finer or coarse graining have the same characteristic, that the states of the system in question revisit the neighborhood of states that they have been in before, which means that I can interpret this trajectory in a probabilistic way, in the sense that if I were to sample me at any random point in time, the density of these trajectories will also be the probability of finding me in that state. So formally, the state space is denoted by x here. The flow through the state space is f, and omega corresponds to random fluctuations on that flow, the temporal derivative being denoted by x dot here. The key result or the key implication that I want to pursue here is afforded by a description not of the states in terms of their flow, but in the probability density over those states, afforded by the Fokker-Planck equation. You may know this as a master equation in discrete state spaces, or the Schrödinger equation in quantum electrodynamics. They're all versions of the same thing, and they just describe not the rate of change of states, but the rate of change of the probability of states given, say, me as a system that has these attracting sets. So we don't need to worry too much about the form of this equation. The crucial aspect of it is that if it is the case that this system has an attracting set and has a non-equilibrium steady state density, then it means that in the long-term future, this probability density will stop changing. And this means that this will be equal to 0. And therefore, we have a solution to these density dynamics, or the Fokker-Planck equation. And that's very interesting, because that solution means I can express the flow as a function of the log probability of occupying any given state given me. I've used the Helmholtz decomposition here just to separate the flow into two orthogonal components, one that depends upon the amplitude gamma of the random fluctuations, and another known as conservative or solenoidal flow that is non-dissipative in the sense, well, let me explain that sense with a bit more of an intuitive explanation of these two flows. Imagine that I placed a drop of ink in a cup of water. Now, normally what would happen if it was a normal ink, then the ink molecules would disperse and dissipate due to the random molecular fluctuations, so that the ink molecules would occupy all of the water or the solvent. So this kind of behavior means that there isn't an attracting set. There is no non-equilibrium steady state density. There is no solution to the Fokker-Planck equation. But what we're interested in is systems that organize themselves so that they possess a non-equilibrium steady state. So a very strange kind of ink that gathers itself together again, as if the molecules were flowing up their concentration gradients. And it is precisely that flowing up the concentration gradients that is given by the solution to the Fokker-Planck equation with these two orthogonal parts. So the gradient flows on the gradients of the log probability that depend upon the amplitude of the random fluctuations are these dissipative flows that maintain and bring states towards regimes of higher probability. And then we have the conservative flow, the solenoidal flow, that circulates upon these probability isocontours here. So that's where the this decomposition comes into play. We'll all be very familiar with this kind of behavior when watching, say, water flowing down a plug hole. So we can imagine that the water flowing down is the gradient flow, and the circulation would be the non-dissipative or conservative solenoidal flow. So that's a brief overview of something quite fundamental about systems that possess a non-equilibrium steady state. I use the word non-equilibrium a lot. Why? Well, that first of all necessitates the presence of this solenoidal flow, but it also speaks to systems that are open. So we're talking about steady states in systems that are not closed, but exchange energy and entropy with some heat bath or heat reservoir, or more generally, some external states. So now we come back to the Markov blanket. So here's our solution to the density dynamics, this sort of generalized gradient flow. This solution also applies to the internal states and the active states. But because these two kinds of states don't depend upon external states, or they're not influenced by external states by construction of the Markov blanket, we can now express the expected flow of internal states and active states as a gradient flow on the probability, or the log probability, of blanket states given me. So the story I'm going to tell is that we can read this as a very elemental kind of perception. And in the same sense, the equivalent gradient flow in expectation for action can be read as action. So what I will do now is just interpret that interpretation from the point of view of a series of normative theories that one can frame under this generic kind of gradient flow. So we've just said that these blanket states are part of an attracting set. So they are attracting states. They are, from the point of view of me, the kind of states that I would expect to occupy. So they are valuable to me in the sense that they tell me that I am in the kind of states that I would expect to be in. So this log probability, when interpreted as value, can be now easily read in terms of normative theories, optimization theories, things like reinforcement learning, optimal control theory, expected utility theory. This quantity I'm also going to approximate with a free energy bound, which we'll talk about later, that is a function of the blanket states and the internal states. So thinking about the log probability of the states I typically or characteristically occupy is nice, because the negative of that has a very specific and simple meaning from the point of view of information theory. It's known as self-information in information theory, sometimes known as surprisal, or more simply surprise. And we're going to equate free energy with that surprise, noting that both internal and active states, autonomous states, are trying to maximize or look as if they are flowing up value gradients or down surprise gradients, means that we can read this dynamics from the point of view of information theory, and we can interpret this in terms of the principle of maximum mutual information or minimum redundancy of the sort proposed by Horace Barlow, and indeed the free energy principle. The average of this surprise or self-information is entropy, which means it looks as if this fundamental gradient flow is trying to, on average, minimize entropy, which means that this is also an appropriate description of the holy grail of things like self-organization, which tries to describe or understand a resistance to the second law and the entropic dissipation, decay, tendency to disorder that you would see in the absence of an attracting set. This is nicely articulated in terms of things like synergetics, and if I was a physiologist, this would simply be a statement of homeostasis, keeping physiological states within viable bounds. So the final interpretation I want to focus on is the interpretation that a statistician would bring to the table. So if I now replace my Markov blanket with a model of how my blanket states, my sensory data, were generated, then this quantity, the probability of some sensory or blanket data given a model, is known as model evidence. So it looks as if the autonomous states are trying to maximize model evidence. And this leads to formulations or normative accounts of certainly brain function in terms of the Bayesian brain hypothesis, evidence accumulation, and predictive coding that we'll see later on. So what I'll do now is try to illustrate the emergence of this kind of behavior and just test that notion of a little Bayesian brain. To do that, I have to construct a simple universe. This simple universe comprises 128 macromolecules. For your interest, they're internal dynamics or autonomous dynamics based upon a Lorentz attractor, and they're also equipped with short and longer range coupling with strong repulsion and weak electrochemical attraction. The details don't matter. You get this kind of behavior with any loosely coupled or sparsely coupled nonlinear stochastic dynamical system or random dynamical system. So I've just integrated some equations of motion to generate this sort of primordial soup, this little collection of molecules all bubbling around together, trying to find some non-equilibrium steady state. The reason that I created this small universe is because I know the coupling or the equations of motion, the flow. I can now go in and identify internal states on their Markov blanket, namely a little particle. And if I can do that, then I can start to ask, does it show lifelike behavior, or does it show this sort of this behavior that makes it look as if it's trying to accumulate evidence for what's going on the outside and maximize the model evidence. So I'm showing here exactly the same solution to those equations of motion, but here I have color-coded the molecules in terms of their role in this partition into external states in cyan, internal states in blue, that are separated by the active states and the sensory states, the blanket states, in red and magenta respectively. And this was easy to do because I just identify say 8 internal states, and I know from the equations of motion, the adjacency matrix, I know the parents, the children, the parents and the children, and I can identify the Markov blanket. And what we can do then is treat this identified set of particular states or states of a particle as a little synthetic virus with a little tail here that's wiggling around happily at non-equilibrium steady state. And now we can start to perform experiments on this synthetic virus and ask, well, do the internal states look as if they are behaving like a little Bayesian brain and appearing to infer the causes of their sensory states? Sometimes in philosophy that's known as self-evidencing, because it looks as if they're trying to maximize the evidence or the marginal likelihood of the blanket states under some implicit model of how those were generated. And indeed, when one looks, one finds very clear evidence that it appears as if the internal states do indeed register or encode or infer, represent things on the outside. So in this example, I've asked, is there any electrochemical internal state that fluctuates with events on the outside, the velocity of external states? And I've color-coded the degree to which the external states could be predicted by a linear mixture of lagged internal states here. And I've chosen a particular example where this external state jumped out of the soup and then was pulled back in again, its velocity being plotted as the dotted line here. And then the prediction is based upon these fluctuating internal states. And we can see by eye that these events on the outside do indeed seem to be registered by fluctuations on the inside. And I use this example because it makes an interesting point. If you look carefully, you can see that the inside starts to show systematic fluctuations before the event on the outside and after. So this begs the question, did the internal states cause the outside, or did the outside cause the inside indirectly or vicariously through the blanket states? And of course, the answer to that question is both, because we have a reciprocal and open exchange between the internal and external states. So what we are looking at here, what we have simulated here, is simply an example of synchronization of chaos or generalized synchrony. So this is the kind of coupling of dynamics seen many years ago and celebrated by Huygens when he noted that clocks, when suspended from the huygens wall or beam, will ultimately come to oscillate in synchrony. And here is a little drawing from Huygens here with two clocks, one pendulum and another pendulum suspended from the same beam. And from our point of view, we can associate one of the pendula with the internal states and the other one with external states, and the beam now constitutes the blanket states. So all we're doing really is saying that there is an interpretation, a necessary emergence of a generalized synchronization between internal states and external states that inherits from the fact that there is an attracting set, a non-equilibrium steady state solution to the Fokker-Planck equation that can be read as a kind of representation that mathematically looks as if it's performing a gradient flow on marginal likelihood or model evidence. I like this little drawing because it illustrates the complete symmetry here, in the sense that I could switch the labels of internal, external, and sensory and active, and say that if you commit to the idea that the internal states are inferring the environment, what's going on out there, then it must also be the case that in one sense, the external states are also learning about you and trying to infer your internal states. And that's an interesting perspective from the point of view of niche construction and evolutionary biology. Anyway, let me just summarize the first part of this talk before we conclude with the sort of the biological version of this story. The existence of a particle implies a partition of a system's states, systemic states, into an internal blanket, namely sensory and active, and external or hidden states. And because active states change but are not changed by external states, they appear to reduce the entropy of blanket states. And this means that action will appear to maintain the structural and functional integrity of the Markov blanket. And in the life sciences, that's sometimes known as autopoiesis, or self-assembly, or self-creation. In computational chemistry, this would be self-assembly. Internal states appear to infer the hidden causes of sensory states by appearing to maximize Bayesian model evidence and actively influence those causes. And in my world, that is known as active inference. There's another interesting, we don't have time to talk about it, but there's an interesting interpretation in terms of information geometry is implied by that generalized synchrony, which has some philosophical implications in terms of beliefs about that are held by internal states about external states, but we don't need to worry about that. Here is a brief interlude. A few years ago, one of my visiting research fellows left to go to America with his wife, and they had a little baby called Kira. And his wife bought Kira a Markov blanket. So this is Kira's blanket, and this is Markov here. So if you want a Markov blanket, you can buy one in America. So let me finish now by repeating what I have said, but using the language of a neuroscientist who's trying to understand how the brain works from a teleological or a normative perspective. And I'm going to unpack that gradient flow in terms of evidence accumulation and predictive coding in neural networks. But to get there, let me just rehearse the perspective from the point of view of psychology. The perspective here probably inherits from the ideas of Plato, but very nicely illustrated by this 16th century oil painter who was famed for painting still life pictures that, when viewed from a different angle or perspective, create a very different visual impression. So if before you saw a bowl of fruit and now you see a face, the key point is that you made that face. The idea is that the brain is a constructive organ, actively creating explanations for sensory impressions, for sensory states of the blanket states. So in a sense, the brain is a little scientist creating hypotheses and trying to explain, in terms of perception, what could have caused that. So this idea, I think, is most clearly articulated by Helmholtz. For example, this phrase, objects are always imagined as being present in the field of vision as would have to be there in order to produce the same impression on the nervous mechanism. This is very closely related to the ideas of psychologists in the 20th century, for example, Richard Gregory, who saw perception as hypothesis testing. Again, this notion that you had to have an explanation on the inside, encoded by internal states, in order to make sense of sense data, the sensory states. For Helmholtz, these were the sensory impressions. This basic idea has been used to great effect, both in neuroscience, but also in machine learning, celebrated by people like Geoffrey Hinton and Peter Dayan, who created a Helmholtz machine as an analog for the Bayesian brain, using Bayesian probability theory, and also borrowing from the work of people like Richard Feynman on variational approximations to this model evidence that underwrites this self-evidencing. From our point of view, this notion of producing impressions on the nervous mechanism is very nice because it speaks to outside or external states impressing themselves, influencing the sensory states of the Markov blanket, that sensory veil. So here cartooned in terms of shadows. So here is our sensory veil, and the internal states, if they behave as if they are trying to maximize or look as if they're maximizing model evidence, then that can be understood as trying to infer what caused these shadows, these sensory impressions. And one might imagine that's quite a difficult thing to understand in terms of neuronal dynamics. In fact, it's actually much simpler than you might imagine. And the simplicity of it rests upon just writing down that fundamental gradient flow in a way that engineers would understand as Kalman filtering or predictive coding, Bayesian filtering generally. And once one writes that down, it looks very much like the equations that underwrite neuronal dynamics in the brain. So let me just take you through that. So here is our gradient flow with the conservative and dissipative parts, here expressed not in terms of the gradients of the log marginal likelihood or log probability of blanket states, but in terms of this free energy band, which we will turn to later, a function of sensory states and internal states. Now I've just rearranged the dissipative and conservative parts into a prediction and an update. So this is the change of my internal states that we think are standing in for states of the world outside the brain that are generating my sensations S here. And this is a prediction. It's basically what I think the states of the world will be at the next time step, given my current expectations. And this is an update term, which is the expressed here in terms of a prediction error multiplied by the amplitude of the random fluctuations. So what is a prediction error? A prediction error can be, well, let's just take this sensory impression here, this sensory shadow. If I had an expectation, an internal state that corresponded to expectation that this sensory impression was caused by a dog, and I had a generative model or a mapping that would generate from this expectation the sensations I would see if this expectation was correct, then I can compare the prediction that is generated by the generative model with the observed sensations to form a difference or a mismatch, and that's just the prediction error. So this solution to the Fokker-Planck equation says that these expectations will be driven by this prediction error so that the prediction errors are then minimized. So I'm going to effectively revise my beliefs to minimize my prediction error. But notice all I'm doing is minimizing my prediction error. I'm not actually, I will never actually know what caused my sensations. It could have been a cat. But if I can explain it in terms of a dog, and I can do that for everything I encounter, that's good enough from the point of view of minimizing this free energy or minimizing equivalently in this form, this prediction error. So that provides a very simple account of self-organization of creatures like me, where we're minimizing free energy or we're minimizing prediction error. And this dual perspective on the ways that we can act and perceive can now be understood as action and perception in the service of minimizing prediction error. So I can either change my mind, change my internal brain states, so that I can generate predictions that are more like the sensations that I'm currently sampling and reduce prediction error through perception, or I can actively resample those data to make my sensations more like the predictions, so that I will literally gather those data that I predict, so that my actions make my predictions come true. And that's the basic story that I want to pursue as a way of understanding both action and perception in the human brain. Just to unpack that a little bit for those people who don't know about neuroanatomy and physiology. Clearly, to create a prediction error, to evaluate that free energy gradient, then I need a generative model that is fit for purpose to explain the kind of sensations that you and I have to explain. And these are generated by a very deep, hierarchically deep generative model that's very, very nonlinear, as illustrated in this example here. So if I asked you to generate some synthetic sensory data of the kind that will be sampled by the center of your retina in your eye, you'd have to understand and write down the causes of those data and how they were generated from those causes. So you'd know, what am I looking at? Where am I looking at it? How are my eyes moving? And then you would write down a series of differential equations and cascade those through a deep architecture to actually generate some sensations or sensory states at the bottom here. So I just cartoon that in terms of a deep generative model that has this hierarchical depth here. We have these hidden external states in the outside world, the random fluctuations cascading down to generate sensations. So how does the brain invert that model? How does the brain make sense of that model to attain this generalized synchronization? Well, we know that it's just the solution to the Fokker-Planck equation for the internal states, which we can now read as a Bayesian filter, where we're trying to minimize the prediction error that just is the free energy gradient. And if we now look at the kind of message passing or dynamics that would fulfill this gradient flow here, then we see the kind of message passing that we actually see in the real brain. So the random fluctuations are replaced by prediction errors, and now the prediction errors cascade back upwards to update expectations that supply better predictions to try and eliminate or explain away the prediction errors given any particular sensations. And this process is repeated hierarchically, so that we have this architecture or this dynamics that is composed of descending predictions and ascending prediction errors, all in the service of trying to minimize free energy or minimize prediction error to attain an explanation for the sensory input at multiple levels of abstraction. Just a note that there are all sorts of interesting aspects of the architecture of generative models that don't just involve hierarchical depth, but also factorizations and factorial breadth in terms of separate encodings of what and where in the brain. But here's a slightly simpler example just to illustrate both this hierarchical these hierarchical aspects of dynamics in the brain, but also to bring back action into the story. So here's a cartoon of the brain as it would deal with vision, active vision. So for example, we could have some sensory information coming from the retina, from the photoreceptors, the light receptors in the eye. It comes into deep brain nuclei. And these deep brain nuclei are in receipt of top-down descending predictions, so that the brain can form a prediction error that is then sent to a higher level in the brain to produce a better expectation that then can explain away the prediction error here. But of course, this expectation is itself being predicted by a higher order or level in the brain hierarchy. So we have this second order prediction error that then can be passed forward to improve or to optimize the expectations at the higher level, and so on to any hierarchical depth that you might want to consider. What I want to do, though, is just consider another kind of sensory input, not from the retina or the photoreceptors, but from the muscles that actively control where I am looking in terms of the direction of my gaze or my eyes. And this information will come in. It will be compared with top-down predictions. There will be a prediction error that could be used to change my mind about where I am looking. But there's a much simpler way, a more efficient way of minimizing this prediction error, and that's to return it to the external states via the active states, so that I can just contract my eye muscles until the signals from my eye muscles match my top-down predictions. So what I've just described is a classical reflex arc, where the reflex arc is fulfilling top-down predictions that are deeply informed by hierarchical processing of other kinds of sensory information. So in neurobiology, this would be like equipping a predictive coding model of message passing in the brain or dynamics in the brain with reflexes to bring action back into play. So I'm going to stop soon and conclude with just illustrating that kind of behavior using simulations. So you can reproduce, using this notion of predictive coding with reflexes, quite realistic behaviors, provided you've got a realistic generative model. So what we've done here is build a little synthetic agent, and this little agent has effectively a central pattern generator as part of its internal dynamics, based upon generalized Lotka-Volterra equations. And what we've done is equip this generative model with the notion, the fantasy, that each point in this abstract space of this attractor here is mapped to a point in Euclidean extrapersonal space, and this point pulls the finger of the agent towards it. So the agent thinks that there's a moving invisible point out there, and it's pulling its finger around. So that's what the agent believes is happening in the environment. And because the reflexes fulfill its beliefs, then the finger will actually follow this invisible imagined point. And of course, the agent is also predicting what it will see. So it sees its finger being pulled around, and it's very happy because it's explained both the proprioceptive and the extraceptive, or the visual information, simply by creating its own sensory input that is consistent with its internal beliefs about how sensory input is generated. I won't go into this, but if you were a neurobiologist, there are all sorts of interesting implications of this very simple construction of autonomous behavior and creating your own sensorium in terms of place field activity, the functional specialization of various neural representations, and interestingly, how we can use beliefs or generative models of our own behavior to interpret the behavior of other creatures like us. So this is the distinction between acting and observing somebody else act, where we just remove the proprioceptive part of the input, but we can still use the same internal machinery, the same neuronal architectures to predict the visual input, and thereby start to infer why you were doing that, because you are producing the same movements that I would do if I was doing that, and therefore I can use my model of my movements to explain your movements. But more mathematically, let's just come back to the computational architecture that we've used to generate those simulations. So we have our Markov blanket, we have external states supplying sensory input. So what we've done here is effectively using that gradient flow, the solution to the Fokker-Planck equation, to minimize a free energy that we can interpret in terms of a Bayesian belief about external states. And then we're using this Bayesian belief encoded by the sufficient statistics that are the internal states, to also explain an equivalent free energy minimization in terms of action, and produce those reflexes by minimizing proprioceptive prediction error. So that's a nice explanation for perceptual inference, building beliefs about the causes of sensations, and then actually generating those causes actively through appropriate action selection. That works for simple behaviors of the sort I illustrated with handwriting previously, but it doesn't explain the kind of behaviors that which we study in human neuroscience. There's a more sophisticated way of understanding dynamics in terms of how we plan. And to put this very simply, if that generative model was sufficiently deep, not just in its hierarchical depth, but also in time, so that very much like that simulated synthetic soup, it actually predicted and postdicted fluctuations in external states. And in particular, if there was a generative model of the consequences of action, I'm now in the position of not just choosing reflexively actions that minimize free energy, but I can entertain different trajectories, paths, or sequences of actions that will minimize free energy or prediction error in the future. And so this leads to a much more sophisticated implementation of free energy minimization that inherits from exactly the same principles of self-organization we've been discussing, but now has a particular kind of depth that we can think of in terms of planning. So here, as before, we take the sensory information in, we form posterior beliefs about the world, and then we use those beliefs to evaluate the free energy that we would obtain under a particular course of action, and then we choose that action to minimize the expected free energy. And this is sometimes known as planning as inference, and I'll show you, I'll conclude with an example of that. But before I do that, this is the last sort of a heavy slide in terms of the maths. I just wanted to unpack free energy and expected free energy in a slightly more intuitive way. And I'm going to use the functional forms of free energy and expected free energy just to make a few links, which some of you might recognize from other fields in terms of, say, reinforcement learning or economics. So I haven't talked much about the link between the log marginal likelihood or the evidence for sensory states previously. I will now do that. So the first thing to note is that I can, these are the definitions of the free energy, and this is the expected free energy. The reason that I've been associating free energy with the log evidence, basically the log probability of some sensory or blanket states given a particular Markov blanket, is that where the free energy is constructed by adding to the log evidence a bound which can never be less than 0, which is a KL divergence or a relative entropy. And that relative entropy is between the true posterior, the probability of external states given sensory states, and some arbitrary approximate posterior denoted by Q, which are my beliefs that are encoded by the internal states. So as I minimize free energy, I minimize this bound, it shrinks to 0, and it becomes a bound approximation to log evidence. In machine learning, this is known as an evidence bound, and they use a negative free energy, so it's an evidence lower bound or elbow. There's another way of rearranging these expressions, which will be more familiar to a statistician, and that's to express the free energy as a mixture of accuracy, the log likelihood, or the expected log likelihood of the sensory data given their causes, and the complexity, the KL divergence between the posterior and prior beliefs about the external states or the causes of my data. So this just scores how much I have to change my mind in updating my prior to my posterior when exposed to data. So this is a complexity cost or an information gain, which means that minimizing free energy means that I want to provide an accurate account of data that is as simple as possible. So this is just an expression of Occam's principle or Occam's razor. What's interesting is that these ways of carving free energy into complexity and accuracy or bounds and log evidence are preserved when you move to the expected free energy. So the expected free energy is basically this quantity, but expected under the outcomes that I predict will happen, given my beliefs about the world and how I'm going to act upon that world. And interestingly, complexity becomes risk, accuracy or negative accuracy becomes ambiguity, and the bound and log evidence become intrinsic and extrinsic value, respectively. So what do these terms mean? Well, let's just ignore extrinsic value for the moment and focus on intrinsic value. So what is this? So it's the expected bound, but now it's about data that are now random variables because they are in the future, which means that we can now interpret this as the mutual information or the information gain associated with the reduction of uncertainty afforded by seeing some sensory data given an action. So technically, it's the expected KL divergence between posterior beliefs about the causes of data with and without seeing the data that would follow a particular action. And in the visual search literature, this is known as Bayesian surprise. And we can also note that this also is simply the mutual information between the causes and the consequences under a particular action. So it's the intrinsic value, also known as intrinsic motivation in things like robotics, scores the information gain, the resolution of uncertainty. It's the epistemic value of committing to that action A. Let me now take a certain kind of uncertainty away from this and ignore the ambiguity. So now I'm going to pretend that I can see the external states directly, that there's an equivalence between external states and sensory states. I can see everything. If that is the case, then what we're just left with is this term here. So what is this term? It's the divergence between what we anticipate will happen given an action in terms of external states of affairs and what we a priori expect, the kinds of states I prefer to occupy, those that characterize my attracting set. So it's just the difference between what I think will happen if I take this action and what I prefer. So in optimal control, this will be KL control. In economics, it's known as risk-sensitive control because there is risk, but there is no ambiguity. And if I now take away the risk as well as the ambiguity, I'm just left with the extrinsic value. So what is this? Well, it's just a score of the degree I expect my attracting states, my value, to be secured by a particular action. And this is just an expression of expected utility theory in the absence of any uncertainty or risk, and is a kind of normative account of behavior you would find in things like reinforcement learning and Q learning and the like. So let me finish with an example. Here I'm going to use visual search and focus on the intrinsic, the epistemic value, the epistemic affordance, and ignore any extrinsic value, and illustrate it with the choice you would have in terms of where will you look next. So say you could only see a small part of the visual scene, and you had a hypothesis that the small limited samples, denoted by this circle here, were being generated by this visual object here. So where would you want to look next? Well, according to this, it's the place that resolves the most uncertainty, that affords the greatest epistemic value or information gain. And we can compute that. We can easily compute this as a KL divergence or a relative entropy for every location in this visual scene, and we can create a map of the intrinsic value. In the visual search literature, this is known as salience, and we can look at this salience map in relation to what actually attracts human eye movements, here from the classic work of Yarbus, showing a remarkable correspondence between the intrinsic value as scored by this part of the expected free energy and where people actually want to go and sample informative, information-rich information. And we can build little agents according to that model that have their salience map, who are now actually planning their eye movements to minimize their expected free energy. And this is the final slide where we've simulated a little agent who has a very simple universe. She can be in a universe where she's looking at a face that's the right way up, on sideways, or an inverted face, but she can only see a very small part of the face and has to decide where to look next to resolve her uncertainty about the three alternative hypotheses here. And this is where she actually looks. These are the updated expected free energy or salience maps here that will change as more information is accrued or assimilated, because then there's a different kind of uncertainty which needs to be resolved. Here are the visual samples following each eye movement, and here are the equivalent sensory streams in real time and where she's looking. And the most important thing here is the resolution of uncertainty as she becomes more and more confident that she is looking at an upside, so looking at a non-inverted face, which is true. This reduction uncertainty, both within and between eye movements, cartooned here. So this is a nice example of responding to epistemic affordances in the game or in the service of minimizing expected prediction error or free energy in the future. More simply making moves on the world to minimize our uncertainty about how the world offers its sensory impressions. So everything I've said is very nicely summarized again by Helmholtz in terms of each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us. That is, their existence in definite spatial relations. So with that, all that remains is for me to thank those people whose ideas I've been talking about. And of course, thank you for your attention. Thank you very much indeed.